Welcome to the Deep Dive, your spot in the AI Paper Podcast series, where we really get into the weeds of the latest AI research. Today, we're looking at a paper that's making some serious waves. It's pushing how large language models reason, especially in tricky areas, like advanced math and coding.
Yeah, this one's definitely caught some attention.
We're talking about DCPO, Dynamic Clipping Policy Optimization. It's work from Shihui Yang and the team over at Baishuan Inc. Now, the core challenge they're tackling here, well, it's about how we train these models using reinforcement learning from verifiable rewards, RLVR.
Right. The existing methods, they often struggled, things like inefficient gradient updates, limited exploration.
Exactly. Because of things like fixed clipping bounds and how rewards were handled. Basically, LLMs weren't learning as efficiently as they maybe could from their own sort of trial and error. So DCPO comes in with these two really smart connected ideas. First, dynamic clipping. It adjusts how token probabilities get clipped based on how rare they are.
Which means more room to explore those crucial, less common tokens.
Yeah. And second, smooth advantage standardization. Just a much smarter way to handle rewards across all the training steps, so you don't lose valuable learning signals.
And the results.
Pretty stunning, honestly. State-of-the-art performance.
Yeah.
Big gains on tough benchmarks like AIM.
AIM is no joke.
Not at all. Plus, way better data use, massively fewer discarded tokens, like an order of magnitude less, and basically double the training efficiency compared to older methods.
Wow.
So for you, our technical audience, this deep dive is all about unpacking how DCPO pulls this off and why it's such a significant step forward for LLM capabilities.
Okay, so to really get this, we need to understand the starting point. We mentioned RLVR, reinforcement learning from verifiable rewards, super powerful for training LLM reasoning. But what was the actual bottleneck? What was holding things back that DCPO needed to fix?
Well, RLVR is key for optimizing LLMs on tasks where you can clearly verify the outcome. Think math problems, writing code.
Right, where there's a definite correct or incorrect. Exactly, and it's a solid framework. But the algorithms often used, especially from the GRPO family group relative policy optimization, they were robust, sure, but they had some, let's say, foundational limitations. These were really hindering deeper, more efficient learning.
Okay, so GRPO was the standard, but it had these issues. What were they specifically? What was slowing the models down?
A big one was something called Entropy Collapse. This is where the advantage values. These are the signals telling the model this choice was good or this one was bad compared to the average.
Crucial signals.
Absolutely crucial. They decay towards zero, especially later in training. And when that happens, the model essentially stops getting useful feedback. The gradients just vanish.
So it just stops learning effectively.
Pretty much. And the other key problem was inappropriate weight clipping. GRPO used these fixed boundaries for the ratios of token probabilities.
Fixed boundaries.
Yeah, think of it like setting a very narrow range for acceptable answers. It meant the model often discarded learning signals from tokens that were rare, maybe a bit unusual, but potentially really valuable for finding diverse solutions.
So it couldn't really explore the less obvious paths.
Precisely. It really limited the discovery of novel solutions.
Okay, that makes sense. So if GRPO had these problems, what came next? I think the paper mentions DCPO Dynamics Sampling Policy Optimization. What did that try to do?
Yeah, DCPO was a direct attempt to fix GRPO's issues. It brought in a clip higher strategy, basically relaxing the upper clipping limit to try and fight that entropy collapse.
Okay, loosen the reins a bit.
Exactly. And it also used dynamic sampling, which filtered out samples where all rewards were the same, trying to ensure every training batch actually had useful gradient information.
Sounds like sensible steps. Did they work?
They helped, but you know how research goes. DCPO introduced its own set of new problems.
The classic whack-a-mole. Solve one thing, another pops up. What were DPO's new challenges?
Right. First, there was response level inefficiency. That dynamic sampling, while ensuring valid gradients, actually slowed down the training convergence quite a bit because it ended up filtering out a lot of data.
So less efficient overall.
Less efficient in terms of data usage, yeah. And second, and this is really key, the token clipping deficit. When the Baishuan researchers looked closer, they found that the best clipping bounds aren't fixed at all. They actually need to vary for each individual token.
So even DPO's smarter fixed bounds weren't granular enough.
Exactly. They were still applying a sort of one-size-fits-all approach, just slightly adjusted. It wasn't flexible enough to really let the model explore effectively at that fine-grained token-by-token level.
Okay, this really sets the stage for DCPO.
Yeah.
So facing these ongoing challenges, the Baishuan team didn't just tweak things again. They seem to have rethought the fundamentals of exploration and learning.
They really did.
And it comes down to these two main innovations. Let's start with the clipping. How does DCPO completely change the game there? It sounds crucial for exploration.
It absolutely is. The first big idea is dynamic adaptive clipping, or DAC. Remember the problem. Fixed clipping, no matter how you set it, just holds the model back, especially in what they call low probability regions, areas where the model isn't very confident yet.
Right, the places where potentially new, interesting solutions might hide.
Exactly. These rare, often high entropy tokens are critical for complex reasoning, but fixed clipping essentially tells the model, nope, stick close to what you already know. DA flips that script.
How does it work? How does it adapt?
It's actually quite neat. DCPO adjusts the clipping bounds dynamically, but it does it based on the token's own prior probability. That's the QX, the probability, the old policy assigned to that token.
Okay.
So the core logic is tokens with a lower prior probability, the ones the model is less sure about, get wider clipping bounds.
So more freedom where it's less certain.
Precisely. It gives the model way more room, more space for exploration right where it's needed most in those uncertain, potentially innovative areas.
That feels like a really fundamental shift. It's not just a parameter tweak. It's like saying, we trust you to explore the weird stuff because that might be where the gold is.
That's a great way to put it. Think about learning a really complex skill yourself. Fixed clipping is like getting the same narrow feedback whether you're a beginner or an expert on a specific move.
Right, not very helpful if you're struggling with one particular part.
Exactly. Dynamic clipping, DAC, gives you much more leeway, a wider feedback window, specifically on the parts where you're weak or unsure of those low probability tokens. It's mathematically designed to encourage learning right there.
So there's some math behind how those bounds are set.
Yeah, it uses a probability-dependent constraint. Basically, the range Rx can vary within expands as QX gets smaller. So lower prior probability means a potentially bigger update is allowed. There's also a hard cap, Rmax equal 10, just to keep things stable and prevent updates from going completely wild.
Smart. Okay, that's DAC. Super interesting. What about the second innovation? Smooth Advantage Standardization, SAS. What problem is that designed to solve?
SAS tackles a really critical inefficiency in how rewards are used. Traditional methods, like in GRPO and even DPO, they standardize rewards only within the current training batch or step.
Okay, what's the issue with that?
The problem arises when, just by chance, all the responses generated for a specific prompt in that single batch get the same reward. Maybe they were all correct, maybe all incorrect.
Right.
When that happens, the advantage calculation, which relies on the difference from the mean reward in that batch, becomes 0 for every single response.
Zero advantage. So no learning signal.
Exactly. The model gets no gradient, no update, nothing. It's like that whole batch of generated data was just wasted, even though the model did expend effort generating it. Plus, these zero advantage steps create fluctuations that can destabilize the whole training process.
Wow. Okay, that sounds like a huge waste of compute and data. Yeah. So how does SAS smooth this out?
DCPO's approach is to standardize the advantages not just based on the current step, but across cumulative training steps. It aggregates the reward information from all the responses generated for a prompt over time.
So it builds up a history.
Precisely. It keeps track of the overall reward distribution for that prompt. Then it calculates two potential standardizations, one based on the current step and one based on the cumulative history.
And how does it combine them?
It uses a clever trick for stability. It picks the standardized advantage value, either the step-specific one or the cumulative one that has the smaller absolute value. IU, J, min unu, J, u a total J is the notation.
Okay, why the smaller absolute value?
It helps prevent excessively large updates and reduces variance, making the training much smoother and more stable. The big benefit is that even if all rewards in the current batch are identical, the model can still learn based on how those responses compare to the historical average. No more wasted data.
That sounds much more robust. It leverages the entire history, not just the snapshot of the current batch.
Exactly. It preserves those valuable learning signals and boosts data efficiency significantly.
And you mentioned there was a third, maybe more subtle piece related to how the loss is calculated.
Yes, that's the only token mean or OTM loss calculation. This addresses some lingering issues with how previous methods average things out.
Okay, what were those issues?
Well, GRPO used sequence level mean, SLM. It averaged the loss across the entire batch of sequences. The trouble is, this dilutes the importance of individual responses. A really good or really bad response just gets lost in the average.
It weakens the signal.
Right. Then DCPO tried token level mean, TLM, averaging across all tokens globally. But this had a different problem. It could mess up the relative importance of responses within the same prompt, especially if they had different lengths.
How so?
A much longer response, even if its average advantage per token was lower, could end up having a bigger impact on the total loss just because it had more tokens. You want the quality of the reasoning, the advantage, to drive the update, not just how verbose the model was.
That makes perfect sense. You don't want length to dominate quality.
Right.
So how does OTM fix this?
OTM calculates the mean loss across the tokens within each individual response separately, so one OI sum. Then it aggregates these response level losses.
So it respects the boundary of each response.
Exactly. This preserves the relative importance structure among different responses to the same prompt. It avoids the dilution problem of SLM and the length bias problem of TLM. It ensures the gradients are driven by the actual advantage calculated for each specific response. Plus, unlike some methods, DCPO's loss isn't explicitly constrained by KL divergence.
Okay, so we have DC for smarter exploration, SAS for stable and efficient reward use, and OTM for accurate loss calculation. Quite a package. How did it actually perform when they put it through its paces? What did the experiments show?
The setup was pretty comprehensive. They used several Quen 2.5 models, ranging from 1.5 billion parameters all the way up to 14 billion, so covering different scales.
Good range. What about data and tests?
The training data was a mix of about 25,000 math problems, combining existing datasets like Math DCPO and Math levels 3 to 5. And for testing, they used some really tough benchmarks: Math 500, AMC 23, and importantly, AME 24 and AME 25. These are known for being high-difficulty mathematical reasoning tasks.
All right, AME is definitely a serious challenge. How did they measure success?
They used two main metrics: AVG at 1, which is your standard greedy decoding accuracy, just taking the single best answer, and AVG at 32, where they averaged the accuracy over 32 sampled responses from the model.
Okay, why AVG at 32?
That one's really important for assessing robustness and stability. It tells you how reliably the model can produce correct answers when you give it multiple chances, which is often how these models are used in practice. You sample a few times and pick the best.
Got it. So what were the headline results, especially on those tough A benchmarks?
The results were really strong. DCPO consistently performed better than, or at least matched, the other methods across all the models and all the benchmarks. It showed broad effectiveness.
Okay, consistent performance is great. Any standouts?
Definitely. The performance on the AVG benchmarks using AVG at 32 was particularly impressive. This really highlights the robustness. For example, get this. The DCPO 7B model hit 38.8 on AME 24 AVG at 32.
And how did the others do?
GRPO was at 32.1 and DPO was 31.6. So a pretty significant jump for DCPO.
Yeah, that's substantial. What about the bigger model on the hardest test?
On AME 25 AVG at 32, the DCPO 14B model scored 19.00. Compare that to GRPO at 10.5 and DPO at 15.3.
Wow, almost double GRPO's score.
Exactly. It really shows that DCPO isn't just improving the average case, it's significantly boosting the model's ability to generate correct answers reliably, even when sampling, which is critical for real-world use. More diversity, more reliability.
That's a key point. You also mentioned a huge drop in token clipping earlier. Let's talk about the token clipping ratio, TCR.
Right.
What is that metric showing?
So the TCR is just the percentage of tokens that get ignored during the update step because their probability ratio falls outside those clipping bounds we talked about.
Right. Tokens deemed too different from the old policy.
Exactly. Now, in methods like GRPO and DAPO, this ratio could be quite high and often unstable, meaning lots of potentially useful information was just being thrown away.
And DCPO?
DCPO was remarkably different. It maintained a very stable TCR, and crucially, it was an order of magnitude lower than GRPO and DAPO.
An order of magnitude? That's huge. What's the implication of keeping so many more tokens involved in the update?
It's profound, really. It means more complete sequences contribute to learning. But more importantly, as the paper puts it, it frees up more space for the model to explore the diversity of rare tokens.
Back to those low probability, high entropy tokens.
Yes. We suspect these are often the key drivers of complex reasoning. By not clipping them away unnecessarily, DCPO allows the model to actually learn from these nuanced exploratory steps, rather than being constantly pulled back to the mainstream, safer predictions.
So it's learning from a richer, more diverse set of internal experiences.
That's a good way to think about it.
Okay, so fewer tokens clipped. What about entire responses? Did DCPO make better use of the generated data overall? You mentioned the response utilization ratio, RUR.
Right, the RUR. This measures what percentage of the generated responses actually contribute to the update, meaning they had a non-zero advantage after standardization.
And how did GRPO fare here?
GRPO was surprisingly inefficient. Its average RUR was only about 44.6%. Think about that, more than half the responses it generated were essentially useless for learning under its own rules.
Over half. That's incredibly wasteful.
It really is. DCPO, on the other hand, achieved an average RUR of around 70% after the first training epoch. That's an absolute jump of nearly 28% compared to GRPO.
Massive improvement in data efficiency. How did DPO fit in efficiency-wise?
DPO actually struggled here too, despite its attempts. The experiment showed it needed 3 to 5 times more generated responses and double the GPU hours to achieve the same number of parameter updates as DCPO.
Wow, so DCPO is not only getting better results, but doing it much more efficiently in terms of data and compute?
Definitely. It's leveraging the data it generates far more effectively.
And one more piece on the training dynamics, stability. How did DCPO affect the model's entropy? Did it avoid that collapse issue?
Yes, the entropy trends are very revealing. GRPO, as we discussed, often showed a sharp drop in entropy that's the collapse, leading to less diverse outputs.
Right, it gets stuck in a rut.
Pretty much. DPO managed to keep entropy high, but it fluctuated wildly, suggesting instability.
Not ideal either.
No. DCPO, however, found a sweet spot. It maintained a moderate and well-balanced entropy level. The curve was much smoother.
So stable exploration.
Exactly. It balances exploring new possibilities without becoming chaotic and refining what it knows without becoming too rigid or losing diversity. And this balanced entropy was even more noticeable in the larger models.
Okay, so it seems like a really well-rounded improvement. We've got these 3 core pieces: OTM loss, SAS standardization, and DC clipping. Did they run tests to see if each part was truly necessary, like Oblation Studies?
They absolutely did. That's crucial validation. They ran tests on the Quen 2.5 Math 7b model, systematically adding each component OTM, SAS, DIC individually to the GRPO baseline.
And what did they find? Did each one pull its weight?
Yes, conclusively. Each individual component provided a distinct benefit, improving performance over the basic GRPO. OTM helped, SAS helped, DAC helped.
So no single silver bullet, but each piece contributing.
Exactly. And importantly, the combination of all 3, the full DCPO pipeline, consistently gave the best and most stable results.
So it's a real synergy between the parts. They work better together.
Absolutely. It validates the whole design. Each innovation tackles a specific weakness, and together they create a much more powerful and efficient learning process for the LLM.
All right, so wrapping this up, this deep dive into DCPO. Dynamic clipping policy optimization really paints a picture of a significant leap forward, doesn't it? Moving past some major hurdles in how we train LLMs for complex tasks.
It really does. DCPO tackles those core limitations of older RLVR methods head-on. The innovations in adaptive token-level exploration with DSC and the much more efficient response utilization from SAS and OTM, it's a fundamental improvement.
And just to recap the key takeaways for you listening. We're seeing state-of-the-art results, especially on tough math problems. That huge 28% absolute increase in response utilization, training efficiency practically doubled compared to DPO, and that order of magnitude drop in discarded tokens.
Yeah, the numbers are impressive, but the bigger story, I think, is why. It's about enabling a smarter, more efficient learning process at a really fundamental level. That ability to learn from rare high-entropy tokens coupled with the stability, it really unlocks more reasoning potential.
Which points towards more sophisticated and, crucially, more reliable AI reasoning down the line.
Exactly.
So, connecting this to the bigger picture, here's something for you to think about. DCPO has shown remarkable success in mathematical reasoning. Where else could this kind of optimized reinforcement learning make a huge difference? What other domains demand that complex reflective decision-making?
Maybe things like scientific discovery, complex strategic planning, even generating highly sophisticated novel code. The possibilities seem pretty broad.
Definitely food for thought. We really encourage you to check out the paper itself. It's available on GitHub. See what you think.
Let us know your thoughts too.
Thanks for joining us for this deep dive into DCPO. We'll catch you next time with more from the cutting edge of AI research.